My name is Jiaqi Gong, and I'm from Department of Electrical and Computer Engineering, University of Virginia. Today, my topic is Reconfigurable Differential Accelerometer Platform for Inertial Body System Networks. We are working in this project, a see-through project. The project is going to provide a sub-powered body sensor network for healthcare in the future. So we are trying to build a bridge. We are trying to build a bridge between the doctors and the patients. So especially for inertial body sensor network, we are using accelerometers, gyroscopes, integrated into the sensor node, and then put it on the patients. Then the doctor, then the sensor node get the data from the gyroscope and the accelerometer about motions of patients. Then submit the data to the data server. We have real-time signal processing to diagnose the disease and the motions of the patients. Then we send an alert or a message to the doctor that the doctor to choose the right therapy for the patients. This is a totally closed loop between the doctors and the patients. That's our goal. Here is the left side. The left side is our current version inertial sensor node. So what's the most challenge? It's the lifetime. Right now, our current version body sensor node, especially the inertial sensor node, we have two versions. First one is use Bluetooth channel. They can be used in lab, and that the doctor to get the signal real time and then give the diagnosis at the real time. But we also have a micro SD card as the storage of memory of the motions of the motions. So the micro SD card version, they have much higher, much longer lifetime than the Bluetooth version. But there is one question, is the gyroscope question. So we can see from here, when the gyroscope is off, the inertial body sensor node have a much longer lifetime because gyroscope is the power consumption of gyroscope is in milliamp and accelerometer is in microamp scale. Actually, yesterday I heard a lot of new design about gyroscope and new gyroscope sensor design, but no one concerned about especially power consumption of the gyroscope. So what we do? There is some researchers from navigation systems. They are also want to get rid of gyroscope. So they design this kind of gyro-free inertial measurement unit. This kind of inertial measurement unit can get 6 degrees of freedom sensing without gyroscope. They use 4 accelerometers together. Here is accelerometer A, B, C, D in a very specified spatial configuration together to replace the gyroscope. Here is an example of navigation guys. They design this kind of very big gyro-free inertial measurement unit. The size is half meters. So can we use it in the body sensor network that the patient will carry this heavy unit? So our design is going to our motivation is going to design a gyro-free IMU for body sensor network. So there are two challenges. First one is the smaller accelerometer displacement. As what I showed before, with the 4 accelerometers, they need a specified spatial configuration. So it means 2 accelerometers, they need to separate a particular distance. So the smaller displacements will get very low signal to noise ratio. The second one is we need to characterize the human motions. So it means we need to new signal models for filtering because we just focus on the body motions, not on others. We want to design a very unique sensor for human beings. So what do we do? First one we answered as a reconfigurable differential signal conditioning. For second question, we developed a model for zero mean stationary first order Markov process. First one, I want to review the measurement model of the Gyro-free IMU unit. Why I call the differential accelerometer platform. Here we can get the angular information vector from the 4 accelerometers. But from here we can see here is the differential angular velocity. It's not a direct angular velocity. Here is the multiply of angular velocity. Here is the square of the angular velocity. So from here we can get some angular information, but we cannot get directly the angular velocity just as the gyroscope. So what do we do? Firstly, we need to collect this kind of information. So we can see from these equations there are two differential signals. This equation is z-axis differential signal between accelerometer A and C, and this one is the differential signal between accelerometer A and D. So we build a differential accelerometer platform to get the differential signal between from all the accelerometers. So why the signal and noise ratio is a big problem? Because they are very closer. The two accelerometers right now in our design just 2 centimeters. Because 2 centimeters just as big as this watch, you can wear it on your very, very comfortable. So we want to design a very small size. The small size means the noise, we need to analyze the noise. And also there are 2 types of noise. First one is the noise from accelerometers. The accelerometer have mechanical thermal noise and electrical thermal noise. And another type of noise is noise from misalignment of the accelerometers, because we need to put the accelerometers in different place. And also there is another one is the signal is very weak because the distance is very small. So we use a differential amplifier to raise the signal to noise ratio. We use the low part filter to filter the mechanical noise. And also we build a closed loop between the signal reconstruction to the differential amplifier, because we can reconfigure the circuit and then to raise the signal to noise ratio. Here is the differential circuit. Here we can reconfigure the gain of amplifier and the bandwidth of the filter, and also the resolution and the sampling rate of ADC. Signal construction. We gather the data and then we go into extended common filter to factorize the transmission matrix between the sensor model to the information model. So that here is totally a closed loop between the sensor and the information processing. And then we model the body motions as zero mean stationary first order Markov process, because our human motion is very special, because we don't have much energy to move our bodies. Every time we move our body parts, actually we want to find a stationary status. So that's why the signal is zero mean almost. From here we can see here is a working scenario. We use the working signal. We can see that all the signal is stays at the zero mean, and also is first water Markov process. So we designed this simulation platform to refine the reconfiguration process. Here we simulate the misaligned noise in the body motion trajectory and the thermal noise in the accelerometer IMU simulation. And also we build a feedback between the signal conditioning data generation with the signal reconstruction algorithms. So what's the experiment? What's the experiment results? Let me introduce the scenario firstly. The subject's right foot is equipped with the proposed differential accelerometers. The right foot trajectory is this line, and I show you the separated trajectory of accelerometers. There are two steps of the subject is walking. So the different colors to indicates the trajectory of different accelerometers. And what's the estimation results? Here is the pitch roll three direction of the gyroscope angular velocity. So from this picture we can see that estimation results and ground truth, they are totally matched together. And I will show you the estimation errors. So we can see here is still very large, but let me compare them together. We can see here, angular velocity, they are stay at positive and negative, almost 500 range. But the estimation errors remains in 5 degree range. So currently, especially for our experiments, we have a lot of medical applications on gate analysis. So this kind of signal estimation is still sufficient for our gate analysis. And also we build a hardware demonstration prototype, use the off-the-shelf components. Our proposed prototype is 1.4 milliamp, and this is another commercial is 4 milliamp. But right now we use the commercial accelerometer scale. It consumes 300 microamp. Actually, current commercial analog device companies, they released 2 microamp accelerometer right now. So if we replace the 2 microamp accelerometer with this one, it means our proposed prototype will be staying 20 microamp. So that's our goal. Conclusion: we make gyro-free IMU for body sensor networks possible. We use reconfigurable circuit, signal modeling for human motion. Our future work, there is a big part is integrating MEMS and stimulus to further reduce power consumption. Just what I mentioned in the last part. That's my presentation. Thank you. Any questions?